So let's take a look at this question together. It says that one object is thrown vertically upward with an initial velocity of 100 meters per second, and another object with an initial 10 meters per second. So they're both thrown straight up with two different velocities. One of them is 10 times larger than the other. It's asking what's the maximum height reached by the first object compared to that of the second object. Well, best way I think to start this problem is to draw a picture, because that I think is the best way to solve all these problems. It's got some initial velocity. It's going to go up and it's going to reach some max height. I'm going to call this max height my final position. And I'm going to say my initial position is at the ground, and that up is a positive y direction. And I'm not going to solve it for the 100 or the 10. I'm going to solve it for the general case of an upward thrown ball. So I'm going to actually solve both these at the same time. Only at the end will I start to throw in numbers and see which one wins and by how much. We know that the 100-meter one is going to go higher, just how much. So the way I'm looking at it is I have an initial position, an a final position, an initial velocity, and I know that my acceleration is equal to minus g. This is g in the downward direction. I say it's a minus g, 9.8 meters per second squared for g, negative because it's opposite of my coordinate. My coordinate is positive up, g points down. So the kinematic equation that I remember, actually let's do this in the y direction, so my y values. Y final is equal to y initial plus v initial t plus 1/2 a t squared. All right, let's see if we can eliminate some stuff out for both these cases. It starts at 0. So my y final, my max height, is equal to 0 plus v naught t plus 1/2 minus g t squared. Just substituting in my minus g for this equation. Okay, now we run into a problem. We run into the problem of, I don't know what time is. I don't know how long the object is. If I know how long the object is in the air, then I could use the velocity and figure out the difference of the heights. Actually, I could figure out how high this object goes, how high the other one goes. It's not important that I know that information to figure out how much higher, but I could get it. I need to bring some other information in because I don't like this time. So I'm going to bring in the other equation. So this was my first of the two kinematic equations. I'm going to use a second kinematic equation, and that's the v is equal to v naught plus at. At the maximum height is when the velocity, the final velocity, is 0. So 0 is equal to v naught plus negative gt. My acceleration is still the negative value. I started with a positive initial velocity. So this says that v naught over g is equal to t. That's really nice because now I'm going to plug this result into this equation. So y final, what I really want to figure out, my final max height, is equal to v naught times t. Well, t is nothing more than v naught over g. I just said that in the previous equation. Plus 1/2 minus g, 1/2 minus g, and t squared. So I'm going to get v naught over g quantity squared. And now I have to do some reducing. This is v naught squared over g plus, actually it's minus, I'm going to bring this minus sign outside, 1/2, I have a g g squared on bottom. So I get a g factor of g on bottom, 2 on bottom, 1 on top. It leaves me with 1 on the bottom. And I get this v naught squared on top. So I have v naught squared over g minus 1/2 of the same quantity. So this is just v naught squared over 2g. One full value of v naught squared over g. I subtract off 1/2 of value of v naught squared over g, and I'm left with my final y velocity, or y position, is equal to v naught squared over 2g. All right, I ran out of room on that page, so let me grab some more paper, new clean sheet, and we'll pick up where we left off. So we left off with our y final is equal to v naught squared over 2g. All of our minus signs disappeared. This is nice. Our velocity is positive. Our g is a positive 9.8 meters per second. The minus sign we took care of already. So that means this is going to be a positive value. That's good because we assume it's going to get to a larger value, a higher value. All right, so now let's figure this out. So our max height, I'm just going to call this now just y. So y1 is equal to our initial velocity 1. This is going to be the 100, let's do this. Y of 100, the 100 meter per second thrown one, is the 100 meter per second squared over 2g. And we know that the y10 is equal to our 10 meters per second, or our 10 meters per second quantity squared over 2g. And I want to know how many times larger. So really what I want to know is y100 over y10. How much larger is this one than that one? How much higher did the 100 meter per second one go than the 10 meter? It's a ratio problem. So all I'm going to do is just going to substitute in what my equations are. v100 squared over 2g all over v10 squared over 2g. Well, this is something over 2g. This is something over 2g, so they cancel. So this is v100 squared over v10 squared. So it's really just the ratio of v100 over v10 quantity squared. I know that this value right here, the 100 and the 10, that this ratio is a value of 10. This is no units whatsoever because it's 100 meters per second divided by 10 meters per second. It turns out to be a unitless number, but the ratio is 10. The velocity is 10 times larger for this one than it is compared to the first, which means my ratio of my max heights of the 100 over the 10 is a factor of 100. So if I look back at my original values, it says how much higher does the 100 go than the 10? The 100 goes 100 times more. It's only 10 times larger its initial velocity, but it goes 100 times higher. Kind of an interesting result. But we had to work through the problem. I worked through the general case, being very careful of my minus signs, and then just solve the ratio problem at the end.